All right, welcome everybody. This is going to be the first part of Chapter 7's Section 1. There's going to be more than one video for Section 1 because Section 1 covers quite a bit of information about naming binary ionic compounds. And so in order to, of course, start that, one of the things we just want to introduce is the idea of a chemical formula, because this is one of the two versions of what we're going to be working with in this particular chapter. The first version is, of course, going to be the chemical formula, where we see an atom is represented by a symbol with a subscript number. The number that follows the atom is, of course, the number of those particular atoms that is in this molecule. So, for instance, a C8 means there are 8 carbon atoms. With H, that's also hydrogen. And there's an 18 after, which means that this particular molecule is bonded with 8 carbon atoms and 18 total hydrogen atoms. This is going to represent a single molecule of a compound. Doesn't mean that when we put this in a beaker that there's only one of them. It just means that each individual unit, or molecule if you will, is going to have the composition of 8 carbons and 18 hydrogens. So with that, we're going to talk about how to write these chemical formulas and how to name these chemical formulas. In this video, we're just going to cover simple binary ionic compounds. Some things that we are moving towards is using the polyatomic ions to do this particular activity. So when I say I want you to have your polyatomic ions memorized, I mean it. You are going to take polyatomic ion quizzes next week, as well as naming quizzes starting next week. So this week we spend time actually learning how to do it. Next week we spend time taking quizzes over how to do it. But in particular, what we're going to do is we're going to see that chemical formulas are going to be simplest ratios. In other words, the lowest number we could ever have in a chemical formula is a 1, and we can never have anything but whole numbers. So when we write out different atoms, or when we write out different chemical formulas, we're going to see that sometimes we have atoms that have subscripts that follow, which mean, for instance, with Al2, that there are 2 aluminum atoms in this particular molecule. We're also going to see that in this particular case, we have a polyatomic ion, which is in parentheses. When we write in polyatomic ions, they're always going to have parentheses around them. And what this means is that there are 3 SO4 units attached to this particular molecule. Now, one of the things to note is that every atom in this particular formula has a subscript after it. The Al has a 2, the O has a 4, there's a 3 after the entire polyatomic ion. The one that doesn't is the sulfur. And what is understood is that if there is no subscript, that it is automatically going to be 1. So anytime we see an atom that has no subscript following it in a chemical formula, please make sure that you remember the subscript is automatically assumed to be 1. Now, in this particular type of formula, this is an ionic compound because we have a positive ion, in this case it's going to be aluminum, and we have a negative ion, which in this case is going to be the polyatomic ion itself. Now, when it comes to naming, we're going to start with what we call monatomic ions. In other words, individual ions that are not polyatomic in nature. So this means anything from the periodic table that can be found in a chemical formula is going to be referred to as a monatomic ion. Now, many of our different ones are going to be able to gain and lose electrons. And we're going to see here a little cheat sheet that some of you have seen before in what we call the most common ions that these different atoms are going to form based on where they're located and their electron configurations. So ions that are going to be formed from a single atom are going to be what we call monatomic ions. Now, in this particular example that we have nitrogen. Nitrogen has to gain 3 electrons to become the nearest noble gas. So the most common charge on nitrogen and the atoms that are in that column is going to be 3-. Now, some of them are going to form covalent bonds, but for us, we're not going to talk too much about covalent bonding quite yet. First, we're going to try and get ionic naming down first. All right, so here are some of the rules for identifying elements' names within chemical formulas, okay? The first is that if they are cations, so positively charged, we simply just name them by the name of the element itself. So for instance, a positively charged potassium, positively charged magnesium are going to be referred to as potassium cations or magnesium cations. Now, for anions, so negatively charged things, what we're going to do is we're going to drop the ending of the element's name and we're going to add the ending "-ide", IDE to the end of the root name. So, for instance, with fluorine, we are going to drop the INE and we're going to add IDE instead. With nitrogen, so nitrogen would be the name of the element, we are going to dash away the OGN, if you will, and we're going to leave behind IDE instead. All right, so now, of course, we have our first question for your lecture quiz. Please go ahead and write down the question number. So this is question 1. And then go ahead and write down your answer, A, B, C, or D. When you're done, you want to go ahead and move on to the next question. Again, write down question 2, and then write down your answer, A, B, C, D, based on what we've talked about. Okay. It occurs to me that I didn't talk too much about platinum 2 and platinum 4. These are going to be ions from your book that are considered transition metals. And we'll talk a little bit about these here in a second, actually. But basically what this is saying is that platinum and platinum are both going to have positive charges, and the charge that they are going to have is given in the parentheses. So for instance, platinum 2 and platinum 4. All right, so some common monatomic ions. So these are all going to be based on where they're located. You have these charts in your book that kind of tell you, okay, everything in this column has +1, everything in this column has +2, everything in this column has +3, and then -1, -2, and -3. I find it a lot easier to learn the layout of the periodic table to memorize where things are going to be. The other types that are not going to be common are going to be these guys. So these are the transition metals, and transition metals can have several different charges. As you can see, vanadium itself can have a 2, a 3, and a 4. So we do not learn common charges for D block elements. In fact, we're going to learn a system of naming that involves using this little parenthesis with a Roman numeral to determine what the charge is. And we're going to learn how to use the anion that it's attached to, or the polyatomic ion it's attached to determine what the charge on the actual metal is. For now, what I want to show you is what we call the most common way of identifying the common charges for different elements on the periodic table based on their location and just their location. So anything in group 1 over here, as you can see, is going to have a +1 charge. The exception to group 1 is going to be hydrogen. Hydrogen can also be a -1. So on this particular diagram, you see hydrogen over here in group 1. You also see it in group 17 or 7A, if you will. From there, if it's in group 1, it's going to have a +1 charge, or most commonly it will form a +1 charge. If it's in group 2, it can form a +2 charge. Then we skip the transition metals. We just talked about how they can have multiple different charges per atom. So we skip the transition metals and move over to the main group P block, where in the first column, the most common charge that these things will form is a +3, so boron, aluminum, gallium, etc. And then in the next column with carbon, these can form a +4 or a -4 charge. For the most part, when we talk about this particular column, a lot of times we'll just skip it, mostly because these tend to form molecular compounds only and not ionic ones. And so when we say charge, we're really saying that sometimes these things can have a charge, but not commonly. And you'll notice that there's things like tin and lead in this particular column. Anything that is not a non-metal, for the most part, can have multiple charges. As we saw in that previous diagram, tin has a common +2 or a +4 charge. And so these particular elements, the 6 or so that are here, are not going to follow the rule of +3, -3, +2, that kind of thing, okay? These are not going to have common charges that make sense with where they're located. And just keep in mind that that's because technically these are metals, not non-metals or metalloids, okay? All right, so then in our next column, in the nitrogen column, we have a common -3 charge, because if it gains 1, 2, 3 electrons, it becomes neon, the nearest noble gas, and the same is true of all of the elements in this particular column. So the most common charge they'll form is a -3. Then with oxygen, again, 1, 2, gain 2 electrons becomes a -2 charge. So everything in the column with oxygen is going to have a common -2. And finally, of course, the halogens, which is on here labeled 7A, but on our periodic table, we say group 17. They are going to only have to gain 1 electron to become the nearest noble gas. gas, so their common charge is -1. So we want to make sure we practice +1, +2, +3, skip, -3, -2, -1. I usually skip because a lot of times, like we said, these things don't form ionic compounds, and this particular naming that we're learning is going to involve common monatomic ions in ionic compounds. All right. From there, we're going to talk about the simplest type of compound, which is a binary compound. Oops, sorry. So these binary compounds are going to be composed of a positive and a negative. And remember what we just talked about when it comes to the cations and anions and their naming. A cation just takes the name of the element, and an anion drops the ending and adds IDE. And depending on the different molecules that you're talking about with anions, the ending might just sound weird. So for instance, bromine becomes bromide, which is very common, but nitrogen drops a lot of its name and becomes nitride. Oxygen becomes oxide, and so on and so forth. So when we discuss those different types of ions, it's very helpful to have a list of the different types of endings that can occur. And that is something that we did just see over here when we were looking at the negative charges and main group elements on this particular table. So these tables do have uses because they give you the name that you're going to be using to actually create your formula or your name of your chemical formula. However, they are kind of harder to understand where the charges are come from, which is why I prefer this specific diagram. Okay, so when we're naming these binary ionic compounds, we want to make sure that we balance charges. So in other words, then the magnitude of the positive charges must equal the magnitude of the negative charges when they're all added together to create a neutral ionic compound. Down here we have magnesium bromide, which is going to have the magnesium ion, which locating it on the periodic table puts it in column 2, which means a common 2+ charge. Locating bromine, which is going to be bromide in our compound, we see that it is in group 7A or 17, which gives us the -1 charge. That -1 charge has to be balanced out by the +2 charge. We're going to learn a shortcut for writing these different formulas. Basically, what you have to do is just the crisscross method. And so this is how we're going to go through and we're going to do it. We're going to practice with something called aluminum oxide. So we know that aluminum, based on where it's located, would have a common 3+ charge, and we know that oxygen would have a common 2- charge. So the first thing we're going to do is write out the symbols. Then from there, we're going to cross charges. We're just going to take the numbers of the charges, not the positive and the negative, and we're going to crisscross them. Doing that forms a neutral compound. So we're going to take the 2 from the oxygen charge and we're going to make it aluminum's subscript. And we're going to take the 3 from the aluminum's charge and we're going to make it oxygen's subscript. In doing so, I create a neutral compound, Al2O3. If you go through and you actually do the math here, since there are 2 aluminums that are 3+ charge, that's going to be 2 times 3, which is 6. And there are 3 oxygens, which are -2 charge. That's going to be 3 times 2, which is, 3 times -2, which is going to be -6. +6 plus -6 should equal 0. Because remember, our goal is to create a neutral compound. Okay, so there's a couple of different steps to follow. And these are written out in your book in multiple ways. You need to be doing that reading and making sure you understand what you're working through. In the case of something like iron, you'd have to be given what the charge is, and you'll start seeing these things that say iron parenthesis 3. The thing in parentheses is a Roman numeral, and the magnitude of that Roman numeral is going to be the magnitude of the charge on these types of compounds. These have to be present. These Roman numerals have to be present for our transition metals, and only our transition metals, so that we can actually write out our final formula. All right. This whole thing that we're doing is referred to as nomenclature. So the act of forming compounds, given names, or forming names, or writing names, given chemical formulas is referred to as nomenclature. And there's several different types of nomenclature. This first type is very simple, binary ionic compound naming. It is not a specific type of nomenclature, it's just the term nomenclature applies to what we're doing. The next type of nomenclature we're going to talk about is the stock system, and that's going to focus more on those parenthesis charges near transition metals. So this is what we call type 1 binary ionic compounds. This is the very first thing that we cover in the naming realm of things. We're going to get all the way through naming transition metal compounds, and then we're going to add the polyatomic ions into the mix, which is why you need to have them memorized. All right, this is our last particular question. I want you to write the formulas for both A and B. One is the addition of calcium and iodine. So remember, go through and follow the steps. You're going to write out the charges on each one first, then you're going to crisscross them. The second one is going to be potassium and sulfur. Again, write out the common charges first with each one, and then crisscross and write the final formula. When you're done, that is the end of this particular video. Our next video will cover the stock system of nomenclature and using Roman numerals to help identify charges of transition metals. Have a great day.